Assuming that you're ready, Marc, I'd like to welcome everyone back to the third and final talk of Marc Hoyois on framed correspondences. Welcome.
Hello, everyone. So the topic for this last lecture is algebraic cobordism, and more specifically a framed model for algebraic cobordism. So, and I start with a little picture here. So it's a picture of a cobordism, of course, between these two circles and this circle here. Yeah, the point I want to make is something about this A1 localization functor. And so here, PQSM stands for proper quasi-smooth. So it's not very important what this is, but this is a moduli stack of schemes, a moduli stack of proper quasi-smooth theorized schemes. I mean, it's natural from the perspective of algebraic cobordism because these are the types of schemes that give rise to algebraic cobordism classes. Yeah, so if you have such a proper quasi-smooth scheme of dimension n, it has a cobordism class in MGL upper 2n comma n of whatever base you're working over, using, for instance, the transfer from the first lecture. But the main point is this A1 localization functor. So remember, this is a functor which makes a free-sheaf A1 invariant, and it's given by this formula, a geometricalization of this simplicial space. Well, if you think about what this space is, this is like a cobordism space for these types of schemes. Yeah, so a point in this space, well, it's just such a scheme, but a path is in this space in our cobordism between two such. Yeah, so it's a family parameterized by A1, giving a path between the fiber over 0 and the fiber over 1. So just like in this picture. All right, so this is like a 1 simplex in here, and and a path between paths in this space, the cobordism between cobordisms is something parameterized by a affine plane, and so on. Yeah, so if you did this in algebraic topology with the real line instead, you would precisely get these cobordism spaces. I mean, that's one way to define these cobordism spaces that appear, for instance, in the cobordism hypothesis in algebraic topology. So it's a very naive analog of this construction of the cobordism space in algebraic topology, where you simply replace the real line by the affine line. And so I just wanted to mention this interpretation of this LA1 functor, especially when you apply it to a free-sheaf, which is like a moduli stack of geometric objects of some sort. Then this LA1, you should think of it as forming the cobordism space of such geometric objects. Right. Now, so remember from last time, we have now this infinity category of framed correspondences between smooth schemes, and there's a forgetful functor to the 2 category of finite symptomic correspondences. So this one is just a 2 category. So this functor is just to forget the framing and just remember the fact that the left morphism in the span is finite symptomic, which means finite flat local complete intersection. Okay, so now there's I guess 2 theorems I want to mention. So theorem A. I'm going to fix an integer greater than or equal to 0. So first part is for every scheme S, if we take the n-fold T suspension of MGL over S, this is the framed suspension spectrum over certain free-sheaf with frame transfers called FQSM upper n. So this is an equivalence in SH of S, which remember, so here I'm using this reconstruction theorem, which tells me that the Motivic spectrum is the same as a framed Motivic spectrum. So the left-hand side, the right-hand side is a framed Motivic spectrum, but and just identify it with an ordinary Motivic spectrum. Well, so this free sheaf FQSM upper n, so that's a free sheaf whose value on X is the infinity groupoid of finite quasi-smooth derived X schemes of relative dimension minus n. So if you prefer, of codimension, and subscript n stands for the codimension. Right, so I did mention a little bit this notion of quasi-smoothness. I mean, I don't want to say much more about this, but just remember this is the analog. I mean, this is also called local complete intersection. But in the context of the Voevodsky scheme, well, it's called either quasi-smooth or local complete intersection, depending on who you ask. But yeah, these are just things in the derived context. Quasi-smooth things are just things that are cut out by some equations in something smooth.
Yeah. Mark, can I ask a quick question? You hear
Yeah.
me? Is this you don't need proper for this? You don't need quasi-smooth proper derives X schemes? Or?
Well, they are finite, so.
Oh, finite. Yeah, right. Sorry, I missed finite. Sorry, thanks.
Yes. Yeah, so this is similar to what I had up here, except that the P is now an F here. Right, and so this is a pre-sheaf which has, it has frame transfers, and in fact the frame transfers don't depend on the frame. So it's just a pre-sheaf with finite symptomic transfers, in fact, but I can regard it as a pre-sheaf with frame transfers. Right, and let me mention that the case n equals 0 is, so if you just plug in n equals 0, you just get the stack of finite symptomic schemes, which appeared last time. So in other words, when n is equal to 0, these derived schemes are actually underived. So they're just finite flat local complete intersections. Okay, and then second part of this now is just basically specialization of the first part to the case of a perfect field, in which case you can say something about the underlying space of these Motivic spectra. So if case perfect, yeah, let me say something about the case n equals 0 first. So loops infinity of MGL is going to be given by this formula. So this is the general formula that you get for loops infinity of a framed suspension spectrum over a perfect field that I explained last time. So you start with this stack of finite symptomic scheme, which is a monoid and the disjoint union, and you take the group completion, and then you A1 localize or kind of form this cobordism space, so the interpretation that I explained here. And then the Zariski locally, this is the infinite loop space. Now, if n is at least 1, then we can also, well, so we're going to have a similar formula for the infinite loop space of the n-fold suspension of MGL. In this case, I'm going to put the Neshitov localization of A1 of this FQSM to the n. Right. So the reason I put Neshitov localization here is that I don't put the group completion here, as you see. So if I just use the general formula, I would have to take the group completion of this thing, and then Zariski unification would suffice. But it turns out that I can kind of trade the group completion for Nisnevich unification if I want. Yeah. So the main point is I can this Nisnevich sheaf is actually connected. Yeah, and I mean, the things that are connected, they're already a group-like. I mean, pi 0 is already a group if it's connected, so you don't need to take the group completion. Yeah, and of course, a posteriori, I mean, this side here we know is n-1 connected. It's by Morel's connectivity theorem. Right. Yeah. Okay. And then that's theorem A, and then theorem B. I mean, I guess I only talk about the proof of theorem A, but theorem B is a closely related theorem. So again, there's one statement of a general base, which is that for every scheme S, there is an equivalence of symmetric monoidal infinity categories between modules over MGL, SH of S, and Motivic spectra with finite symptomic transfers. So yeah, so what I mean by this, I mean, this is just, we repeat the construction of SH or of SH framed, but using this category of correspondences instead of this one. And now again, in the case of a perfect field, you can say something more stronger, and so it is perfect. So there's a similar equivalence of symmetric monoidal categories between now very effective MGL modules and Motivic spaces with finite symptomic transfers, which are also group-like. Yeah, so this part two basically is a combination of, well, the general result of part one plus a cancellation theorem for this category. So this is equivalent to saying that the cancellation theorem holds for these Motivic spaces with finite symptomic transfers. Right. So any questions on the statements of these theorems?
I have one simple question on theorem A, part one. So, I mean, this seems to imply that if you have a class of a proper quasi-smooth morphism that has a negative relative dimension, then you can somehow move it to be finite up to cobordism.
Yes.
Right? Is there a simple construction for this, or?
Yes, I mean, because everything is actually cobordant to the empty scheme in negative dimension. So, I mean, this thing, right? This, as I said, these spaces are connected. Yeah. So if you just take by zero of this is trivial. So I mean, concretely, this means that if you have, something of negative relative dimension over a field, then it's always cobordant in a naive sense to something empty. Because this, if I evaluate this on a field, I get a space which is n-1 connected.
Okay, thanks.
And I mean, and it's a pointed space. The base point is the empty. Right. Okay, so the key, so the main ingredient in the proof of theorem A is to understand, to obtain framed models for Thom spaces of vector bundles or Thom spectra of virtual vector bundles. And okay, before, let me just mention this. So I state all these results for MGL, but there's entirely analogous results for any other Thom spectrum that we'd like to think about. So, Marc. there are analogous theorems for example, MSL, MSP. The sphere spectrum itself, etc. So for example, for the sphere spectrum, this is saying, so what is the sphere spectrum version of theorem A? It's the same thing where you replace this by framed such things. Yeah? And here a framing, so is a framing of codimension n. So the framing of such a finite quasi-smooth derived schemes would be a trivialization of the virtual tangent bundle. Rather, it's a path between the virtual tangent bundle and minus n in the K-theory space. That's what a framing of dimension minus n would be. And then in this case, that would tell you that if you take the infinite loop space of the n-fold T suspension of the sphere spectrum would be this cobordism space of these framed finite quasi-smooth things. For MSL, the relevant additional structure is now just an orientation, meaning trivialization of the canonical sheet. And for MSP, you would look at these finite quasi-smooth things whose virtual tangent bundle as a symplectic structure, and so on. Okay. So frame the models for effective Thom spectra. So this is essentially the sphere spectrum case of the theorem A, I guess. Okay, so let's consider a smooth S-scheme X and K-theory element of rank greater than or equal to 0. So then I'm going to define a framed presheaf, X from XC framed. So as a presheaf with frame transfers on smooth schemes. So I send U to the following. So spans like this, UZX, FG, where so F is finite quasi-smooth. And I have a given isomorphism between the relative tangent bundle of F and minus G upper star C in the K-theory space of Z. Right, so there's a minus sign here because this C has a non-negative rank, but of course the relative tangent bundle of F has non-positive rank because it's finite. So TF is rank 0 or negative. So yes, a remark is that in the case where the rank of C is 0, then then the Z is actually going to be an underived scheme. Then Z is underived. So, and for example, so the case when C is actually equal to 0, this recovers then. So X0 frame is just the presheaf with frame transfers represented by X over S. Right, so you should think of this more general thing as being some twisted variant of this. Well, at least if C has rank 0. Right. So of course, I mean, because this is an infinity category, it's not so easy to just define a pre-sheaf on that, right? So this, just writing this down does not, you know, define a pre-sheaf on this infinity category. So there's some technical work is needed to make these things precise always. But you know, at the end of the day, anything that, you know, ought to be definable, you know, can be defined. I mean, and you just have to get used to the formalisms that you need to, you know, define functors out of an infinity category like this. Right. Right, and now, so the theorem is the following, that these XC framed pre-sheaves, they are frame model for the Thom spectra of these Cs. So the Thom spectrum of C is equivalent to the framed suspension spectrum of this pre-sheaf. Right, so this is equivalence again in SHS, which is the same as SH framed S. Okay, so let me briefly indicate the strategy of proof for this. So we first start with the case when Xi is actually a vector bundle. Suppose C is some actual vector bundle V over X. Yeah? Vector bundle on X. And so in this case, I mean, the difficult part, yeah, so there's two parts of this theorem, and one part you have to construct a map between these two, and then show it's an equivalence. Yeah, I mean, both tasks are non-trivial. So we start with the case of vector bundle, and then in this case, we can define a map as follows. For my vector bundle V, I can look at the zero section. So I can look at this span, this kind of correspondence from V to X. Now the zero section, of course, is a finite and quasi-smooth morphism. It's a local complete intersection. And if I look at its tangent, its virtual tangent bundle, well, it's minus, well, it's canonically minus V, the virtual tangent bundle of the zero section vector bundle. Right, so I have a canonical such equivalence. And so this datum defines precisely a point in this pre-sheaf X comma V framed. Yeah? So it defines a V valued point of X comma V framed. Right, so this is the datum that we need here. Right, and moreover, what happens if I restrict to the complement of the zero section inside of V? So if we look at the complement of the zero section here, well, what's the restriction? Of course, the pullback here is empty. Pullback here is the empty scheme. So that means that this composite here is zero. I mean, zero, so the zero is, in this pre-sheaf is exactly the empty span here. Right. Remember, a pre-sheaf with frame transpose is always an infinity space. Yeah, so it's a commutative monoid, and the commutative monoid structure, if you look at this pre-sheaf, is given by taking disjoint unions of these z's. That's what gives the commutative monoid structure. And so the zero element is the empty z here. In fact, well, because the K theory of the empty scheme is contractible, you see the connected component of zero in this pre-sheaf is actually contractible. So there's no question of having to choose a null homotopy or something like this. So this composite is 0, so you get an induced map from the cofiber, which is the thumb space, like so. And this is a comparison map that we're looking for in this case. Right. And so in this picture, the right-hand side here is a pre-sheaf with frame transfers. So I can also add, by adjunction, I can add frame transfers on the left-hand side as well. So let me do this. So I'll look at the associated framed pre-sheaf. Yeah, so this just means, well, in this notation, this is V, 0 frame. Yeah, so this is just the pre-sheaf represented by V and the category of frame correspondences. Okay, so we've defined this map down here. Right, and then, so this is the definition of the map, and then we have to show it's an equivalence. So in fact, so this is now Motivic equivalence. And so the proof of this uses a moving lemma of Garkusha, Neshitov, and Panin, which is over fields. But I mean, this is a kind of statement that can be reduced to the case of a field. I mean, we want trying to show a symmetric equivalence over any base S, but it turns out, yeah, you can reduce to the case of a base field, and then over the base field, well, you can even reduce to the case of an infinite base field. And in the case of an infinite base field, you use this moving lemma, which shows that this is a Motivic equivalence. Okay, and then, so this is the case of a vector bundle, and then somehow you need to generalize this to the case of a virtual vector bundle. And this is essentially formal. So the main point is that you use the fact that, so the K-theory functor is the same as the Zariski sheafification of the group completion of the pre-sheaf of vector bundles. And so basically, if you look at this thing as a functor of V, let's assume that this X is actually the base that we're working over. And so this is a functor of the vector bundle V with values in the category SH over X. And of course, this thumb spectrum, as a thumb spectrum over X, this is in the Picard space of SH. Yeah? So it's an invertible Motivic spectrum. And also this functor is monoidal. It takes a direct sum of vector bundles to the tensor product of the spectra. And it lands in the Picard space. So it factors uniquely to the group completion of the monoid of vector bundles. Yeah, I mean, this is also how you construct the J homomorphism from the K3 space to SH. So it's the same construction. So using same idea, you can now extend this. We can now think of it as a natural transformation in B, or in the pair X comma B. And it's suitably compatible with a symmetric monoidal structure. So you can extend kind of this Motivic, well, you can extend this morphism to the case where when you replace this vector bundle by a general virtual vector bundle. And then to check it's an equivalence, well, that's easy because any virtual vector bundle is Zariski locally an actual vector bundle. Yeah, so you already know it's an equivalence of vector bundles, and it's easy to deduce it's an equivalence for virtual vector bundles as well, as long as you have a comparison. All right. Okay, so this is more or less how the proof of this theorem goes. Okay, and now let me go back to theorem A and explain how one obtains theorem A1 from this. Well, I already kind of explained how 2 follows from 1. I mean, follows from these general facts about perfect fields, together with an additional computation that this thing is connected. But, so I'm only going to talk about the proof of part 1. So this Motivic spectrum MGL can be written as this over S. So we use the following description of this Motivic spectrum MGL. It's a co-limit of all Thom spectra as X ranges over smooth S schemes and C ranges over K3 elements of rank 0 over X. So this is one way to present this Motivic spectrum MGL. So, I mean, this is not the usual definition of MGL. The fact this equivalent was proved by Tom Bachman and myself in our paper about norms in Motivic homotopy theory. And this is a description which is useful for some purposes. For example, from this formula, it's more or less formal that this has a canonical infinity ring structure, which is something which, I mean, with the usual definition of MGL using Thom spaces or Grassmannians, you need some kind of tricks to get an infinity ring structure on that, and it's not. I mean, you can also do it, but somehow it's not. Doesn't appear to be particularly canonical. You have to do some kind of tricks to get the infinity ring structure. Whereas this formula somehow is a very symmetric formula, which is from which symmetric monodal structure is formal. Sorry, the infinity ring structure is formal. Anyway, I mean, that was the motivation we had in this work on norms, but it's also useful now here. So using the previous theorem here about the framed models for these Thom spectra, we can rewrite this co-limit now as, well, we directly obtain it as a framed suspension spectrum of the co-limits over all these X and X's of these framed pre-sheaves X, C framed. So this is by the previous theorem. Right, and so now the claim, yeah, I guess I'm only doing the case n equals 0 of theorem A at the moment. So I'm trying to prove that MGL is a framed suspension spectrum of this stack of finite symptomic scheme. And so basically the claim is that this is actually the stack. So now we have to make a computation of this co-limit. So there is there's kind of a more or less evident map from these, for any of these XC frames as forgetful map to the stack of finite symptomic things. So there's a forgetful map like this. Right, so how does this go? Well, an object here in this pre-sheaf is, well, it's a span like this. Using X together with an equivalence between, well, I guess a minus sign, minus like this. I mean, oh, in this case, C has rank 0, so the minus sign does not matter too much. And yeah, so you just forget, you just remember this F. Just remember the morphism F. That's a finite symptomic morphism from Z to U because C has rank 0. Yeah? So the virtual tangent bundle is rank 0. So this morphism is actually a finite symptomic. And now the claim is basically this forgetful map is an equivalence. And so to do this, you compute the fibers of this map. So if you take the fiber at some point, which is some f here, some finite symptomic f from u to z. So what is a fiber? Right, well, I can write the fiber as a colimit like this as well. So colimit are all x c's of the following datum. So you have a morphism, you have this morphism G from Z to X. And this trivialization of the virtual tangent bundle. Right, so I mean, this is just a space of all such things which give you this given Z to U down there. So, okay, now we can make a small computation about this colimit here. I can exchange some exchange of colimits. Let's see how this go. Yes, I can rewrite this as colimit of all x in Sn over S, and all maps G's from Z to X of yeah, so I just put this guy in the colimit, and I'm gonna put this C up here, and do this kind of formal exchange here, just rewriting this. And then this becomes, so one way to write is just a fiber over this virtual tangent bundle of the pullback morphism in K theory from K theory of X to the K theory of C from G. Right, so yeah, this is just a formal rewriting of the data that we have here. Because an element in this fiber is precisely this K theory class C together with this isomorphism here. Right, and now I can do, I can also exchange the fiber and the colimit because colimits are stable on the base change. So it's the fiber of colimit over X and G of K theory of X mapping to the K theory of Z. Okay, so what's the point of rewriting it this way? Well, this thing here you might recognize in this colimit the formula for the left-Kahn extension. So this is in fact exactly the value on Z of the left-Kahn extension of the K theory appreciative restricted to smooth schemes evaluated on Z. Right, and this map is just the canonical map from the left-Kahn extension of the restriction back to the original appreciative. Right, and the point, so now the fibers, so we're basically trying to show this fiber is contractible. And now we've written it as a fiber of this, of another map, this comparison map between K theory and its left-Kahn extension from smooth schemes. And so to conclude that this is contractible, so it's not actually contractible on the nose the way that I wrote it, but I claim that this is in fact contractible if Z is affine and I take this colimit here over smooth schemes that are also affine, which is fine because it does not, I mean, in this formula for MGL, I could just use only affine schemes here. That would also work. So it's not an issue. Right, so the key result then is the following proposition about algebraic K theory. Due to Batts and Lurie. So if you have R, a commutative ring, and you look at the K theory functor on commutative R algebras, And in fact, I can even go, I can include derived algebra or simplicial commutative rings. So this functor is Lefkan extended from smooth algebras. Over R. Yeah, so this proposition then concludes the proof because it shows that this comparison map here is actually an equivalence. And so therefore these fibers is contracted. Therefore this map is an equivalence. Therefore MGL is a frame suspension spectrum of this moduli stack of finite symptomic schemes. Right, so this is how this proof goes, and the case, so I did the case n equals 0, but the case for higher codimension is approved in exactly the same way. And here, it's now relevant that we know this Lefkan extension result for derived schemes, for derived.
Marc, are you using homotopy K theory here? Because the Lefkan extension is homotopy invariant, right?
No, Lefkan extension is not going to be homotopy invariant. So this is not homotopy K theory. This is actual K theory. Yeah, so in fact, this result is not true for homotopy K theory because, well, because it's true for K theory, and I mean, at least if R is regular, K theory and homotopy K theory agree on here. So only one of them can be Lefkan extended. So it turns out actual K theory is Lefkan extended. Yeah. So yeah, we really are using actual K theory here, and in fact, yeah, it is also necessary in this whole description of framed things. I mean, if you cannot just, I mean, everything I'm telling you about framed correspondences would not work if you replace everywhere K theory by homotopy K theory. I mean, even if you're over a field, even when you're over a field, I mean, in this framing happens over some Z, which is finite symptomic or something smooth. So the Z itself doesn't have to be smooth. Yeah? So there's a difference between K theory and homotopy K theory, and you actually have to take the trivialization of the virtual tangent bundle in K theory, not in homotopy K theory. All right. Yeah, so let me just mention that the proof for these positive suspensions of MGL is basically exactly the same. I mean, it reduces, again, it reduces to, I mean, it's the same starting from this theorem here. So this theorem works also for X's of positive rank. So of course, you're going to use this case. But for example, the n-fold suspension of MGL is a similar colimit here, but you put the rank is equal to n. Yeah, and then it's the same type of computation as here, and then you use again this result to conclude. And now the Z's that we'll have in this computation will be derived schemes. Yeah, so you really need this kind of the derived version of this result. Okay, so I guess as I think I have time to say something about the proof of this. So let me sketch the proof of the proposition here. So starting from, let's just look at the formula for the Lefkan extension. So if I Lefkan extends restriction to smooth algebras, so it's going to be the colimit K theory of S, where, oops. S is a smooth R algebras, and oh, sorry, I have to evaluate on something. Ah. I don't know, T. These are bad names for algebras, but yeah. So yeah, so this is just a formula for left-hand extension. Yeah? So you have some smooth S mapping to T. The point of writing this down is just to observe that this indexing category here is shifted. So this category has finite coproducts. That's finite coproducts, which are just given by, I mean, the same as in commutative algebras, and just the tensor products of these S's. Hence, is shifted. So this is a shifted colimit. And we also have that, because we're only looking at K3 affine things, and K3 is just a group completion of vector bundles. And now the point is a group completion operation will commute with the shifted colimits. Yeah? So. With shifted colimits. So we reduce to proving an analogous statement for the pre-sheaf of vector bundles instead of K3. Yeah, so suffices to show that this pre-sheaf is left-hand extended from smooth algebras. And for this, so one thing you can do is look at the Grassmannians of n-planes and take a Johanna device over here. Johanna device. So that's an affine. That's an affine bundle whose total space is affine. And then look at the map. So the disjoint union of UKs, k less than equal to n, mapping to vector bundles of rank less than equal to n. All right, so I guess the first step is I can write this pre-sheaf vector bundle as a colimit of pre-sheaves of vector bundles of rank less than equal to n over n. So it suffices to show that each of these is left-hand extended. And then the point is, so this is just a forgetful map. Yeah, I go to a Grassmannian. From the Grassmannian, I just extract the underlying vector bundle. And this forgetful map is actually surjective on sections. It's a section-wise surjective. Why? Because if you just start with a vector bundle here, and because we are only dealing with affine schemes, this vector bundle is generated by global sections. So you can lift it to a point of the Grassmannian. And then you can further lift this point from the Grassmannian to the Johanna device, because again, things are affine. And so this is an affine bundle, and a affine bundle over an affine scheme has a section as well. So this is surjective on sections. Therefore, if I call this map F, that means I can recover this pre-sheaf as the colimit of the check nerve of F. So it's a simplicial colimit of this check nerve. And this, so this is simplicial object now. So this GRN, this is like an int, this is an int smooth scheme. Yeah, it's a filtered colimit of smooth schemes, and so are these UNs, and so are these things here. These are all the smooth int schemes, or smooth int. They're int objects in the category of smooth affine schemes. That's what I should say. Yeah, so. And the same remains true of all the self-intersections when you form the check nerve of this morphism. So you have to take the fiber product of this with itself over this stack, but this is a stack with smooth and affine diagonal. So all the iterated fiber products of these things will still be colimits of smooth affine schemes. Right, so if you combine this colimit with this colimit, you get that this whole pre-sheaf is actually a colimit of pre-sheaves represented by smooth affine schemes, which is exactly what it means to be left-Kahn extended from smooth affine schemes. Okay, yeah, so this is the proof of this result. Okay, so I think, let me just end now with a remark or maybe some speculation. There is in this theorem A, there is this finiteness conditions and everything. Yeah? So these stacks are all stacks of finite things. But as I mentioned at the beginning, in fact, this finiteness restriction is not needed to get algebraic cobordism classes. Yeah? So this general theory of transfers tells you that if you have any proper quasi-smooth schemes, it has algebraic cobordism class. So it's a thing natural to ask, you know, what happens? I mean, are these results still true? You know, if I just replace, if I relax this finiteness condition to a properness condition, for example. So, I mean, there's a lot of natural questions you can ask about this. So let me make a remark. So if you drop the finiteness condition, so let's just look at the dimension 0 case. So then this stack of finite symptomic morphism becomes that of proper quasi-smooth schemes of relative dimension 0. And this is much larger, yeah. I mean, because there's a lot of derived schemes of dimension 0 because you can start with any scheme of any dimension n. Start with any local complete intersection of dimension n. Then, I mean, there exists a derived scheme structure on this, which is quasi-smooth and of dimension 0. Presumably, there will exist many, but a very stupid thing you can do is you can just, if it's dimension n, and you look at the vanishing locus of the 0 function n times. So you cut out the vanishing locus of the 0 function n times, and that defines the derived scheme structure of dimension 0. But the underlying scheme does not change. Yeah? So the underlying scheme will still be dimension n. Right. So if you drop this finiteness condition, then you open a whole new world of objects here. Yeah, so what can we say about this? We can say very much. So one thing we can say is that it turns out that so if you form this naive cobordism space on this thing, then this is a group on the disjoint union, which is something which is not true for these finite symptomic things. Yes, for these finite symptomic things, you have to group complete it. You have to force it. You have to forcefully group complete it to get this model for the infinite loop space of MGL. Whereas this guy, it turns out, is already a group. I mean, of course, it's not a group before passing to cobordism. Yeah, I mean, this is right. I mean, you don't have negatives for disjoint unions, of course, but somehow up to cobordism, it is a group. And yeah, so I don't know. So it's kind of an interesting observation. And in any case, how does this relate to MGL? Well, we have, of course, we have inclusion of Fsin in this EQSM0. And then, at least conjecturally, there will be a map from this to the infinite loop space of MGL. And this, I mean, this is using the transfers in MGL cohomology, because we know that MGM cohomology does have transfers for proper quasi-smooth morphisms of relative dimension 0. I said conjecturally because, I mean, to actually get this morphism, you also want this to be a morphism of framed pre-sheaves. Yeah, so that's a lot of coherent structure, and at the moment, the construction of these transfers is not sufficiently coherent to actually assert that there exists this map. I mean, so I mean, even though we, at the moment, somehow we cannot define this map, but I mean, it is clear that this map exists. Yeah, it's just a matter of making this construction of the transfers more coherent. Right, and of course, now this composite map here, when you pass to the adjoints, so the framed suspension spectrum here does give you back MGL. So this implies that you get, well, this implies that if you take the framed suspension spectrum of this thing, this has MGL as a retract. It's also an MGL module, so it's yeah. So it's an MGL module that contains an MGL as a summand. And so, I mean, if you're over a perfect field, then you can therefore conclude that the infinite loop space of MGL is a direct factor of of whatever this cobordism space is. And yeah, and again here, the point is we don't need the group completion here because this thing is already group complete. Yeah, so of course the natural question is, is it actually the same? So this we don't know. Okay, so I think that's all I wanted to say. So thanks you for listening, and I will stop here.
Yeah, thank you very much, Marc. I think we should all applaud in some way or another for this beautiful conclusion of the lecture series. Are there any questions?
I have another question. Are you assuming resolution of singularities in order to do your left Kahn extension?
No, there's no assumptions here. You mean in this proposition?
Yeah, because if you take the local ring of a integrally closed point of dimension at least 2, then you have a problem of finding smooth maps to it that are going to cover the closed point.
Right. Yeah. But the left Kahn extension goes in the other direction. Yes? So you have maps. You have maps into smooth schemes, not the other way around. So it's not about mapping smooth schemes into things. It's about mapping into smooth schemes. So this is, I mean, this is saying that if you have any K-theory class on some affine scheme X, then, I mean, in particular, it says that this K-theory class factors, so if you think of it as a morphism from X to K, it factors through something smooth. In that sense. So all K-theory class are pulled back from things that are smooth. In particular, I mean, this is a more precise statement.
Are there any further questions? Okay, if that is not the case, before we thank Marc again, I'd like to remind you that this Thursday, 2 p.m., September the 3rd, there will be the next talk in the Motivic Geometry Seminar by Grigory Garkusha on semi-local Milnor K-theory. So again, thanks a lot to Marc for his lectures.